Hi, everybody. So this talk is intended to be a review of some older work on the relationship between singlets, long strings, and black holes. So the context, first we will talk about this in the context of the C=1 string theory, and that most of the talk will be about this. So this is a non-critical string theory on a two-dimensional background where the worldsheet theory contains the free field describing the time direction, and then a Liouville conformal field theory. And the target space theory is supposed to be a flat space-time with two dimensions. One direction is time, the other is this space direction. And we have in the space direction, we have a linear dilaton, and we have a region of very large string coupling and a region of very weak string coupling. So it's convenient to think of the region, this weak string coupling region, as somehow the boundary. That's where we put the boundary conditions. So this is analogous to the boundaries in ADS-CFT. Then we have, well, one important point is that this linear dilaton has a large gradient, so a string scale gradient. And then in addition, we have a tachyon field that has a non-zero Bev in this region, in this large string coupling region. And this prevents strings from propagating into that region, and strings sort of bounce back from this tachyon wall. I mean, we can say that the tachyon has condensed in this left side region and has removed the left part of the space. So in this way, we get a weakly coupled string theory. The coefficient in front of the tachyon Bev is some parameter we call mu, and this is essentially a weakly coupled string theory whose string coupling is related to mu. So larger mu corresponds to smaller string coupling. Well, what happened here? Here. Now we can think of some approximation to the two-dimensional background. So this is not in principle a good approximation, but we can view a non-critical string background as the usual action, bosonic string action, except that we have a cosmological potential. It's not quite a cosmological constant, but let's say a constant here, which is proportional to the 2D minus 26. And if you solve these equations, then you can find the linear dilaton background. And so on. Here I've set the tachyon field to 0. You can also add the tachyon field if you wanted. Now this is not quite the good way to treat the system, because as we said, the solution is string scale. So we're not justified in keeping just the massless fields. And in fact, these are not propagating fields in 2 dimensions. But anyways, you can go ahead and with this disclaimer, you can go ahead and solve these equations and find that they contain actually a black hole solution, which consists of a 2-dimensional cigar-like region, where asymptotically on the right-hand side, the size of the circle goes to a constant, and we have again a linear dilaton, and so on the right-hand side, it goes back to the same background that we had in the previous transparency. So it seems to obey the right boundary conditions. That's the same boundary conditions as the previous solution. And so in this solution, there is one free parameter, which is the value of the string coupling at the tip. So you can view this in various ways. So if you think you fix the string coupling somewhere far away, then this solution has, let's say, naively, it seems to have a free parameter, which corresponds to making the cigar longer and longer. Okay, so you might think that classically it has a free parameter, an unfixed parameter. Another funny feature of the solution is that it exists only for a particular temperature. So once you put in the parameters of the theory and so on, the size of this circle is completely fixed. Okay, so it's fixed in terms of this d minus 26. Now, as a side comment, I should mention that after some field redefinitions, this solution is just the same as the solution of flat space JT gravity. So by that, I mean an action which is phi times r plus a constant. And that in turn is the same as the near horizon geometry of any black hole. And so the fact that the temperature is fixed is related to the fact that when you go to the near horizon geometry of a black hole, the temperature is somehow just 2 pi, just at the Rindler, just the temperature of Rindler space, and the space is flat. Anyway, so that's just a side comment. But for our purposes, we will focus on this solution. And now, first there were some disclaimers I said here about this action, but by the time we, but however, there is an actual string theory background that has a similar geometry. So this background is found through an algebraic construction. So we think in terms of an SL2 module 1 coset construction. And that in principle, well, that gives us an exact string theory background, so exact in alpha prime. Of course, it just gives us the 3-level solution in string theory, so it's valid for weak coupling. Again, this model has a particular radius at infinity, and we can ask, and of course it has the geometry of the Euclidean black hole, is the same as the previous one, and we can ask how we compute the entropy. Now, in principle, I don't know how to compute the entropy. In principle, we are supposed to vary the radius at infinity, right, and compute the derivative of the partition function. And it would be nice to have a string theory formula for computing that. That is not just the gravity formula, which in this case, we cannot apply the gravity formula directly because it's a string scale background. But in any case, we expect it to go like 1 over the string coupling at the tip of the cigar. This is how we would expect it to go, even though there isn't a concrete calculation computing it directly from string theory. Now we can compare this with the matrix model. I think Igor discussed the matrix model on Monday, and the matrix model, the gauged matrix model of just one matrix, you go to the double scale and limit, and you find that it's described in terms of free fermions in an inverted harmonic oscillator potential. And you can compute the energy, and it really does not scale like n squared or mu squared, which is how you would expect to scale if it was dual to this black hole. So we have an apparent contradiction because we have a black hole background and we don't have the required states in the matrix model. Now, the resolution of the contradiction is that this SL2 module 1 exact stream background does not actually obey the same boundary conditions as the background without the black hole. So this should not be viewed as a black hole that some other possible configuration in the same background. So how can this be? The metric and the dilaton of the gravity solution certainly have the right boundary conditions. These fields do indeed obey the same as the boundary conditions for the original background at finite temperature. So the problem is not with those fields, but the problem lies with a particular string winding mode. So in any black hole background, in any Euclidean, let's say black hole background, the string winding on the thermal circle, Euclidean thermal circle, is not conserved, and the background in principle, well, no, not in principle, but the background has an expectation value for winding operators. And this, if we imagine doing a Kaluza-Klein reduction in the Euclidean time direction, then along the space direction, this behaves like a massive field. And we expect any web that is sourced at the tip to decay exponentially, okay? And that's indeed how we think it behaves for any higher dimensional black hole, and that's actually indeed how it behaves for this black hole. However, the problem is that this decay is not fast enough to be normalizable. It's not fast enough to be a normalizable deformation of the original background. So because the string coupling is becoming very, very weak here, the contribution to the action of any field is multiplied by 1 over g squared and can be large and can in principle diverge. So in this case, it just doesn't decay fast enough to be a normalizable deformation. So we shouldn't view this background as another possible solution given the boundary conditions that we had for the original theory. Okay. Now, as I emphasized in other black holes, we also have this mode, but it's usually a normalizable mode, especially in the gravity regime where the circles are large and it's decaying rapidly. So here it's just the combination of the small radius and the large dilaton gradient that is causing this problem. So I think this is a side comment, but when we talk about gravity solutions which have string gradients or curvatures, the gravity description can be misleading. So even though the geometry looked very similar between gravity and this exact background, the actual physics is a bit different. You get the wrong physics if you think about the gravity description. Now, non-normalizable means that what we are doing is that we are deforming the original model by adding an extra source at infinity for string winding. So you can think of this as a relevant perturbation that we do of the original model, and then we do this relevant perturbation, and the size of this relevant perturbation determines the string coupling at the tip. So in particular, in the gravity approximation, this black hole configuration has a zero mode that corresponds to moving, changing the value at the tip or making the cigar longer and longer. In the exact description for this particular background, the value of the BEV of the winding mode at infinity, which is something we put in by hand from the outside, determines the value of the tip. So we don't have such a zero mode. Okay. I should mention in passing that this SL2 mod U1 background is also describes near extremal phi branes and well, at finite temperature and so on. And in that case, indeed at tree level, we do have this zero mode. So in that case, we can make the size of a circle large for taking a large number of phi branes. And so in that system, we do have that zero mode, and people have discussed, especially Kutaso has discussed the fate of that zero mode. But in this case, we don't have it. So that's also another difference with gravity. So in the matrix model, the idea is that, so there was this very nice paper by Kasakov, Kostov, and Kutaso, who explicitly added this winding mode to the matrix model and solved the matrix model with this addition. So we can say that what we are doing is we are computing the partition function with the addition of this winding modes. And adding the winding modes corresponds to adding these operators in the gauge model. So here we're imagining we are gauging there is implicitly an integral over A in this formula. And we are adding these Wilson line operators. And notice that we are adding them in the exponent here. Okay. Now the full background that they discussed contains 3 parameters, beta, which is the size of the circle, mu, which was the value of the tachyon that we set to 0, and also lambda, which is the coefficient in front. Now notice that in their discussion, they can change the radius. So from the matrix model side, we can change the radius of the background. We expect that should also be true in string theory, but we only know how to get an exact solution for a specific radius and also for mu equal to 0. But we also expect to be able to turn on the tachyon. So the fact that we can turn on the tachyon is perhaps not surprising, but should be emphasized that from the matrix model side, we expect that the radius could be anything, and indeed, in principle, you could find in principle, we expect that for this background, we could change the radius, but only for a specific radius, we know the exact solution. For other radii, one would have to solve the sigma model in some other way. Okay, Now the partition function was found essentially following the following technique. So the basic idea is that this model has some t-duality. So winding is essentially like momentum in the t-dual variables. And then in the t-dual variables, what we're doing is we're adding momentum modes of the massless fields, massless tachyon. And then we use the the usual free fermion picture to add this momentum, which correspond to adding some waves on the Fermi sea. So that's roughly the conceptual idea for how it was solved. I mean, the full details you can find there. They did it in a couple of different ways. And they found some expression for the tree-level partition function. So this is, they found the expression also for mu different from 0, but I just wrote here simply the expression for mu equal to 0. And so it's some function of lambda. And this lambda somehow sets the coupling at the tip. And the relation between lambda and the coupling you can find by basically how this winding mode depends on the radial position and how the coupling depends on the radial position. And by matching these two, you can find that the coupling and the tip squared scales like this. So we get a partition function that goes like 1 over chi squared and has some temperature dependence. So from this, you expect that it should have the expected order of magnitude of the temperature of the entropy. And notice that, as we said before, the beta can be anything. I mean, in principle, it can be outside this regime, but the nature of the solution is different. But beta equal to 3/2 is the value that you get in SL2 mod U1, which is in the middle between these two. Okay. Now,
sorry, Juan, I have a slightly clarificational question. So this winding mode is some massive field that is not visible in the supergravity or the gravity solution that you showed, but just had a phi and a metric.
Yes, exactly, yes.
I see. So it's a massive mode that is turned on the solution. And there's like a one parameters family of
in this discussion. Right.
Well,
okay, thank you.
It's a winding mode of the tachyon, which wasn't written.
Yes.
Right.
Yes,
okay,
it wasn't part of the original action that was discussed here, so it wasn't written here.
Okay, thank you.
Yeah, I mean, if you did, let's say, some kind of dimensional reduction of this in the time direction, maybe you could write a one-dimensional action, perhaps. I don't know how to write a two-dimensional action for this mode.
Can I add a comment on that?
Yes.
If you take the OP between two winding modes, as far as I remember, you create the black hole operator whose non-linear, I mean, if you do it non-linearly, this deformation of the black hole operator, you make this background, right?
Yes, you can think. I think what you're saying, if I'm not mistaken, is that if you add this winding mode here at infinity, so you start with the cylinder and you add the winding mode at infinity. Sorry. I think a calculation that was done in the KKK paper is the following. So you start with the original background with non-zero mu, right? The original background, and then you add this winding mode as a perturbation, right? And then you analyze this perturbation theory enough, and then you manage to resum the perturbation, and then you get the tree-level solution. So that's one thing they did. So that's one way to obtain this background. Yeah, that's one way to think about this background as being generated by adding this relevant perturbation, and then when the flow, I mean, after you flow in the infrared and you resum the whole perturbation series, you get this particular background. Okay, so from that point of view, it's better to start with non-zero mu and then sum in powers of lambda, and then recover, then take mu equal to 0 at the end if you wanted. Okay. Okay. Very good.
Can I make a comment?
Please, yeah.
Yeah. So it's probably worth saying that at this special point, beta equals 3/2, where you have a world sheet theory, there really aren't independent tachyon couplings and black hole background. The theory is described as some SL2 mod U1 coset model, and the winding tachyon and the background metric are two aspects of the same vertex operator. In the same way that the two asymptotics of the incoming and outgoing tachyon are related by the fact that they're reflecting off the wall, the winding tachyon and the black hole are two parts of the same vertex operator. So you can't perturb one without perturbing the other. It's not like, okay, there's an independent, winding tachyon and its OPE contains a different vertex operator for the black hole. It's two parts of the same thing.
Yes, that's an important point. That's an important point. So because winding is not conserved, when you send in a particle, let's say you consider a particular, imagine you turn on here some field, which might or might not have binding at infinity. When you put it in this background, it gets reflected into modes that could have any number of windings, right? So this kind of shows that when you look at this type of problems, you have to consider all possible bindings together, and indeed the value of the value of the dilaton at the tip, which is a closed string mode, is basically the same as the winding we are discussing. So within string theory, they are part of the same mode. Indeed, that's an important point. Okay. Now, usually we consider the gauge model, and the gauge symmetry imposes a singlet state projection. But adding Wilson loops, we can project onto non-singlets. So we have, for example, if we wanted the adjoint, the partition function in the adjoint representation, we would just sum not over the states in the Hilbert space that are singlets, but the ones that are in the adjoint representation. And that's, of course, equivalent to introducing the field A0 and then putting a Wilson line and then taking the trace with some A0 chemical potential, non-trivial background for A0, and then integrating over A0. Now, this type of problems has a standard sort of thermodynamic interpretation where what you're doing is you're adding an extra adjoint heavy particle. While this problem here, its Lorentzian interpretation is not 100% clear because we are adding, well, in principle, we are adding this Wilson line in the exponent. So this is not a completely local Hamiltonian. We could think of it as some kind of chemical potential, but at least to me, it's not totally clear exactly what the Lorentzian interpretation of this is. And presumably the KKK partition function can be obtained by subtable superposition of lambda. I mean, you could in principle expand in lambdas and keep one power. That's a bunch of insertions of this Wilson loop operator. So this would be a very large representation, or at least maybe some sum over such representations. Now, just in order to figure out what, the simplest version of this problem of considering the model in different representations, the Lorentzian problem, is to consider just the adjoint. So that's the simplest non-trivial representation. And the idea is that if we consider the matrix model in the adjoint, we have exactly the same background that we had before, but we have an extra long string that comes from infinity. This is what we expect from the string theory side, where we say that we add a Wilson line corresponds to adding a string. And so we expect such a folded string. And the string again comes from the weakly coupled region. And so the dynamics of this string is that the string tip comes in from infinity and then runs out of energy and then goes back to infinity. maybe I'll say it a little more slowly. So the string tip comes in with lots of kinetic energy, but there's the string that is pulling it to the right. So it loses energy until the energy goes to 0, and then it turns around and starts accelerating in the opposite direction. And most of the time, it just goes basically at the speed of light. So that's the motion of the strings. The energy of the string is infinite because it goes infinitely to the right. We could subtract this infinity, but if we do that, then we get the Hamiltonian, which is unbounded below, because the tip of the string can move further and further to the right, and then that would make the renormalized energy smaller and smaller. But well, that's a feature of this problem. It is still a fine problem to consider. Now, these folded strings arise in other examples of gauge gravity dualities, not just in this example. So, for example, if we added a non-supersymmetric Wilson loop in n equal to 4 super-m mills in the adjoint, we expect a similar folded string and then ending at the boundary of ADS5. Again, a similar feature of the Hamiltonian, renormalized Hamiltonian being unbounded below. Now, you can analyze in more details this matrix model in the non-trivial representation. So I think Igor probably discussed the matrix model in the singlets, which is just a bunch of free fermions. So now the fermions are interacting, and there is an interaction that involves the degrees of freedom of representation. So here pi ij is the ij generator in the representation R. And this acts on, so it's a matrix in the representation R. And so you can think of this as some kind of spin chain, or a model where besides the positions of the free fermions, they have some spin degrees of freedom, and they are interacting through these spin degrees of freedom. The form of this term should remind you of an angular momentum term. So if we had a motion, for example, if we had, this is analogous to the motion of a particle in a plane, where we set, for example, the angular momentum on the plane, then we get a similar 1 over r squared term. And here, these representations are given effectively some angular momentum in SUN. Now, for the adjoint, this can be simplified a little bit further, and it basically, this whole stuff here leads to leading order in the large N expansion. It leads to essentially an additional particle that you have. So besides the free fermion, you have this additional particle that can be viewed as the tip of the string in the string theory picture. And it feels a force towards the region towards higher eigenvalue density. So it feels a force to the right. And so the particle comes in from the left and then goes back to the right. So that's roughly what we get. And in this paper by Witkowski, he solved this problem exactly and found the reflection phase. And that reflection phase can then be matched to a similar reflection phase, which is a function of the energy. And it matches what you get in the string theory side. Now, in principle, you can ask what happens when you have more complicated representations. So in this large N limit, the relevant representations will be representations that will have a finite number of, let's say, boxes, extra boxes here, and anti-boxes. So you can, you can roughly view it as diagrams of this kind. You could put this vertical line here and think of this as, anyway, so now in principle, there is a trick to compute the free energy, the Euclidean free energy for any fixed representation. And so this is, as far as I know, it's not published, but, and I'll tell you why. So there's a trick to compute the free energy, which consists of compactifying the Euclidean circle. Then there is a map between the string bindings you should put and these Young diagrams. And that map is essentially similar to the map between bosons and fermions in bosonization. So under T-duality, so if you start with this Young tableau, so it's like starting with some fermions, then you transform into some bosons, which would be the windings. So you turn on these winding operators, under T-duality, these winding modes become momentum modes of a boson, of a tachyon, and then you can translate those to fermions, so the fermions of the matrix model. And in this whole translation, it looks as if these final fermions in the matrix model end up being, or the T-dual model end up being essentially the same as these fermions. So you can, in this picture, you can read off the momenta of the fermions by looking at the number of boxes. And this gives you the momenta of the fermions in the Euclidean circle, so that they integer along the Euclidean circle. And so this partition function looks a bit like an S matrix, where you have the left moving fermions come from the top here, and the right moving fermions come from the bottom, and you calculate you can calculate it in this way. Now, when you calculate it in this way, we do not seem to get a large entropy for a fixed representation. But there are also some paradoxes with this evaluation. And the main paradox is that the reflection matrix for the fermions is basically diagonal. And because it is diagonal, it's only non-vanishing if the representations are self-conjugate, so that the pattern here of boxes or momenta for the fermions is the same as the pattern you have here in this bottom. So for example, this is not a self-conjugate representation. So you would get zero for it.
Excuse me, Juan, just to interrupt you. You say that nothing is published about this T-dual picture, but we have some set of papers with Ivan Kostov and Sergei Alexandrov where we
thanks for correcting me.
Used these time-dependent backgrounds to describe this T-dual picture in terms of fermions, essentially.
Yeah. Well, that's the trick. Yeah, this trick is not the. Yeah, this trick you had in your paper, right? This translate.
Yes. I think if we are speaking about the same thing. Probably.
Yes. Yeah, I agree. So all I'm saying is that the, well, maybe you had this in your papers already. I don't know. But you can write down an expression for the partition function in a given representation. And it basically looks like a bunch of reflection matrices for each of the fermions. So each of these boxes corresponds to some momentum for a particular fermion, and then you compute the product of all those faces, and that gives you some expression. And here, yeah, if there is a reference, please give us for this. Because,
I will.
But it has a paradox. This paradox. Now, in this discussion, I've ignored the leg pole factors, which is one point that I think recently there was some more progress understanding this, but at the time when I thought about this, I didn't understand it, and I thought maybe there is a subtlety with those, and that's why it's not, maybe this is not exactly correct. But anyway, yeah.
So is this notation something like a composite representations, so that it factors into boxes and anti-boxes? Like we're using in the past for two-dimensional Young mills? Because in some sense, this description holds only for large n, right? Where you can only use boxes and the anti-boxes. Yes. But for finite n, you should take the full Young tableau.
Oh, yes. No, I agree with that. But I think in this context, we're always at large n because we are doing the double scaling limit. So we're always at the very large n.
Yeah. Okay.
Yeah. Yeah, so maybe this might be understood. Now, another thing you can do is you can think about FCCT branes, and those are supposed to be the same as adding some massive fundamentals and anti-fundamentals. And so and there's a parameter mu boundary, which is when basically the mass of those fields, and the brane looks like some brane that comes from infinity, and the tachyon condenses, so the brane stops here. And in this case, you can think about a scattering problem where you send an open string, so a mode here, and the string comes in from the right, and the ends get stuck here and produce one of these long strings that then bounces back off, and so on. And in principle, yeah, so this is a theory that has a nice interpretation, and by taking a large number of these branes, perhaps it's another way to get the background. So I mean, this source for winding that was necessary for the black hole and was studied in the KKK paper. So the conclusions of this part of my talk is that the black hole seems related to the non-singlet sector. I mean, that's very clear. And so perhaps at some high temperatures, there can be condensation of these long strings near the origin that gives rise to something like a black hole. Now, I guess the question is whether this non-singlet theory is integrable. The upside-up harmonic oscillator is integrable, in fact, for any representation, because its energies are all quantized and simple. But it's not clear to me whether this upside-down harmonic oscillator is integrable in non-trivial representations. Now, the integrability might be a double-edged sword in the sense that if it is integrable, we can question whether there will be interesting lessons from black holes. It might be that it is integrable and this background, even though it looks like a black hole, doesn't behave at all like a black hole. That is a possibility. That would be a bit, I would say, disappointing. But if it is not, then maybe we can analyze it enough so as to learn some more general lessons for general black holes. I mean, it might be that even if it is integrable, we can learn how a black hole becomes, I don't know, some other system.
Is there, sorry, Juan, is there any indication from the matrix side that beta is 3/2 is a special temperature, or was this just a curiosity from the worldsheet perspective?
You're asking whether from the matrix model side is
right. So from the worldsheet side, there was this curious thing that we have a cosine model. So from the matrix side, was there anything occurring at that particular temperature that might be a special point where the black hole becomes integrable or something? Maybe it's a question for Volodya also.
Not that I know. So there is a particular power that becomes an integer. So no, I don't know. Maybe Volodya has something more to say about that.
I also don't know. We posed this question many times to ourselves and to the other people. It's not very clear. But another good question is maybe to Juan. Do you think all other R's in this interval also correspond to black hole states, or it's something else?
Yeah, I think, well, there is a question of whether this is really a black hole, right? Whether it has
what else can
properties of black holes as having large entropy or an absorption coefficient for the scattering when you scatter some particles and the Lorentzian signature and so on. Yeah, I would expect them to be all similar, at least within this range.
I think just one
this is what you said in your paper. I'm not. Yeah.
One comment from the past. I mean, from our troubles in the past. You explained how, more or less qualitatively, how to get the results for singlet sector on the trivial, in quotation marks, fermionic background, namely this just the vacuum state of fermions. But the problem is, and maybe it's solvable, integrable, it's too much to say, but at least it may be treatable by large N methods, is to solve the same problem about adjoint on this black hole background. Then we would get hand on maybe on Hawking radiation, all these kind of things. And this calculation is missing, maybe.
Okay, yeah, that's a good idea. Yeah. So what you say is that if we think of, maybe I just repeat what you said in AI, different words. So you consider the scattering of a massless tachyon that comes in and goes out with, let's say, 1 small units of momentum, and then you T-dual the whole thing. And by T-dualing the whole thing, you transform the black hole into some free fermions on a non-trivial background. And but you have some insertion of a small number of representation, let's say the adjoint.
Yeah, then you have to scatter the windings.
Right. Yeah. This could be I mean, one thing is probably goes beyond the adjoint because you need the momentum to be arbitrary, right? So you'll have, but yeah, it sounds like by solving the problem with winding n and winding minus n, right? So it should probably be some relatively simple representations. Yeah, yeah, that could be.
It's a hard but not necessarily unsolvable
problem.
Yeah,
yeah, that's a great idea. Yeah, sounds.
Maybe sorry, just to follow up on Dio's question. I mean, from the TDO sine Vivio perspective, the radius is also not so special, right? Once we imagine certainly deforming it.
No.
But I would imagine that if one considers a scattering of a close string off this black hole background, there's some pole structure on the imaginary momenta that's probably has some special form for the cigar, but not if you deform away from the cigar.
Yeah. Well, that could be. Right.
Yeah, but it's just, I mean, in principle, I think by studying some Lorentzian quantity in the matrix model, one should be able to detect this.
Let me make a comment about the cigar. So I think that something that is special in the cigar, for example, is that if you consider a particle that has some units of winding, and you see how it mixes with particles that have different number of units of winding, then this violation of winding, I think it's by 1 unit. Let's say in the 2-point function, I think, or yeah. Well, I think in the n-point function, there is some violation that is bounded by n, the number of points in the n-point function. And that's, I think, is something special for at this point of SL2 module 1. I think it will not be true in general. So this is in answer to the question of whether there is something special. So I think that there is something special at this point, that the violation of winding is constrained. Okay, I mean that figured in the analysis of ADS3. So the ADS3 background is somewhat similar to this one.
And this would have a simple representation from the matrix side.
No, this is just some statement about the string theory side. That's something that is special there, and presumably in the matrix model that feature should be reproduced. I think it hasn't been looked at as far as I know, and so you could imagine trying to reproduce that and checking that, and that presumably will lead to some symmetry. Perhaps it's a symmetry of the planar. I mean, you would expect it to be a symmetry of the planar theory because it comes from the Kac-Moody symmetry of the worldsheet theory.
It's somehow related to an integrable structure on the worldsheet side.
Yes. Yeah. Okay. So now I'd like to finish. Do I have time still, or? Well, I said I would go for at most 40 minutes, so maybe.
Yeah, keep going.
So we will now discuss some non-singlets a bit more generally. I mean, this is perhaps for a bit more curiosity. So one question is whether non-singlets are relevant, or we can talk about non-singlets in the BFSS matrix model. So the BFSS matrix model is the matrix model for the zero brains is a UN gauge quantum mechanics. And so it's a quantum mechanics with a UN global symmetry, which we then project onto the singlets. So the gauging just consists on projecting onto the singlets. So in quantum mechanics, gauged or ungauged are very closely related. So you can simply consider the ungauge theory. And even if you consider the gauge theory, you can consider non-singlets by simply adding Wilson lines in specific representations. So you can access the non-singlet sector also there. So gauging or non-gauging, there is some method for accessing the non-singlets. So the simplest question is what happens, for example, if you add an adjoint. And the idea is that the background, so the usual background for these zero brains, so here consider the finite temperature where we have a black hole. Then the background has some region here in blue where you can trust the gravity solution, and then some region far away where the gravity solution becomes strongly curved. So by the logic we were talking about before, perhaps it's not surprising that the conjecture here is that the actions will have something to do with these folded strings. But the idea is that the ground, so the folded string, the tip will want to move outwards. And the idea is that when it moves outwards into this strong coupling region, the value that of the energy of this state now is of order lambda to 1/3, where lambda is the g square n is the effective coupling of the quantum mechanics theory, which has dimensions of energy cubed. So the new feature compared to the previous one is that there is an actual energy, that energy cost for putting the adjoint. That in the previous example, there is that energy cost in principle, but it was infinite. Here it is finite, of course, not calculable from gravity. But in this second paper here, they did a numerical simulation and they found some behavior which is somewhat consistent with this. I mean, with the idea that there will be a non-singlet state with this energy.
So in principle, if one had the worksheet sigma model,
yes.
that will be calculable, right? Because it's weak calculable even though.
Yes. Only that it's not calculable in gravity. But yeah, indeed. Yeah, you're completely right, of course. Now, if you consider the ungauge model, you might think that you could wonder whether it is possible to have a D0 brane with only a single string coming, only a string coming in, but no string going out. So usually there is a gauge field on the D0 brane that prevents a string, just a string from ending on the D0 brane. If you have a string ending on the D0 brane, there should be one departing. And the idea is that even in this ungauge model, if you have a D0 brane here in the gravity region, it would still have its own gauge field, okay? So the non-singlets will live here at the boundary. So in some sense, it will look like the gauge fields that live on this D0 brane are really not the same as the original gauge fields of the boundary theory. Side point. Okay, so there is also some discussion of this in SYK or tensor models. So in SYK, there is an ON symmetry that arises after averaging over couplings, but not before averaging over couplings. So in SYK, it doesn't make sense to talk about gauging the ON symmetry. However, in the tensor models, there can be, well, there are in general ON symmetries, and the basic degree of freedom is not ON invariant, so some fermion with several indices, several ON indices, could be various ON indices for ON groups, for example. Now, these fields have low conformal dimensions, and there are order n cubed of them. So one hypothesis that one could wonder about is whether we get a more conventional gravity theory if we impose the gauge constraint, because that would remove a bunch of light fields. And I would say that you still do not get a conventional gravity theory, because the light particles would appear again in the non-singlet sector, and they would appear again if you add a Wilson loop and so on. And so the background cannot correspond to one with, let's say, high string tension. So such a background will be always some low string tension background, regardless of whether you gauge or not gauge. So somehow to get to Einstein gravity, we need a strong coupling, so that you can get this non-singlets a large energy. So in conclusion of this last part of the talk, the non-singlets can always be studied, well, in various examples. And in general, when we are at strong coupling, they have high energies. And in tensor models, of course, the non-singlets are nice because they lead to a simple solution to the model. And so one wants to include them even if we had the gauge model. Even then, we would like to include them to talk about the solution after all the G and sigma variables of the, well, let me just say that the methods for solving the leading order tensor models rely on using those non-singlets. If we gauge them, we would have to add a Wilson line between the bilocal operator that is used to solve the model. Okay, thank you.
Thank you.
Okay.
So, yeah, can I ask why? So it seems like everything we know about the matrix model is telling us that there is no black hole. And so I'm wondering why one persists in thinking that there's a black hole there to be discovered. So the fact that we can change the radius is consistent with the sine-Liouville picture where the topology is a cylinder, but not consistent with the cigar picture. And the fact that you're on the other side of the correspondence principle transition that says that the black hole solution is dominated in the picture of the winding tachyon versus the cigar. It's the winding tachyon picture that's the weakly coupled side of the FZZ duality. So it says that the physics is dominated by that winding condensate and not by the cigar geometry. And I could list a there are additional pieces that I could talk about, but let me just ask why do you have an intuition that there's a black hole there to be discovered?
Well, the main intuition is that there was that cigar solution, and the model with non-singlets looks like it's not free fermions, so it might be a model with some interactions, and so it is possible that for complicated enough representations and so on, you might have some strongly interacting system which displays some of the properties of black holes. Whether the black hole is best viewed as a gas of interacting strings or whatever, I don't know.
How would you distinguish a black hole here from just a Hagedorn gas of these long folded strings?
Yeah, so I think the question is whether there is something which has entropy, which is 1/g string squared, that has some long-lived, that when you send a particle, the same particle doesn't come out. I mean, that the information gets scrambled. Those are some of the features one might wonder where they exist. So the question, I mean, to me, it's not obvious that this is not true. So, and if it wasn't true, then the model might be solvable enough that you can have something which is both solvable and has the non-trivial black hole dynamics, or maybe analyzable, not exactly solvable, but analyzable.
I just worry that everything is so stringy that it would be so. If I have a Hagedorn string in higher dimensions, it's got a lot of entropy, and if a closed string excitation was absorbed into it, it would scramble too. So I guess what I'm saying is there would be an additional burden that if you found something in these folded strings to show that it had anything that resembled black hole physics, or how you would, the question would still arise, how do I distinguish what I'm getting out of the analysis from a black hole versus something just very stringy?
Maybe you won't, and I'm not sure you will, but I think that there are some qualitative features like the entropy and the scrambling and so on that you don't need to talk about the background to find. So these are some signatures that you could expect. I mean, those signatures are not present in the singlet sector.
Can I make a comment on that? So, if you consider the scattering of a closed string kind of bouncing off the wall in the presence of a thermal bath of long string, I would think if you take the right limit, one should be able to recover the end continuation of the reflection coefficient on the cigar, which will have the features of you know, absorption by the black hole and things like that. And also related to something else Emil just mentioned, you know, the sine duo is the T duo, so there's no contradiction between the linear topology of sine duo and the topology of the cigar. And the belief is that in the stringy, in some regime of stringy temperature, you should be able to, basically we know that the cigar is T duo to the sine duo at a specific radius. And because we think in some regime, the sine duo can be deformed, the cigar should also be deformed, just that that cannot be characterized by the semi-classical nonlinear integral model.
Could I make a comment on the last part of the talk about tensors? And
yeah,
I was basically thinking about the comparison with good old ON vector model, where the solution also basically uses the non-singlet objects. Like we start with 4-point function of phi A, well-known bootstrap for that. So for tensors, I completely agree. What's been done so far is very similar. We don't solve it in terms of just purely singlet objects yet. But for the ON vector model, we basically know that only the gauged version is obviously dual to higher spin theory. I mean, it's a highly curved background, but so I'm basically wondering, I mean, if you look at the tensor model, and it could be that there is a special place for the gauged model nevertheless. And one sign of it is that if you look at the splittings within the singlet sector, we think that they're tiny, they're exponentially small in like e to the minus n cube order. Well, I think the splittings between singlets and non-singlets, while small, they're only of order 1/n. So there is still some kind of hierarchy of splittings, and I mean, all of this is, we have no idea what the dual of the gauged or ungauged tensor model full dual would be, but there could still be a special place for the gauged model, I think, similarly to the ON vector model.
Yeah, I mean, I would say that even in the ON vector model, you could define in the model some operators which contain, let's say, phi, Wilson line, and phi, right? That would.
Yeah, it would be interesting to search for what they mean in the higher spin dual, right?
Yeah, well, I think they're present in the field theory, and they would mean that you have some additional, let's say, strings that come from infinity or something like this in the spin dual.
So something similar could be with tensors. I mean, maybe there are membranes or something like that.
Yeah, but it's a string that is very light, so it doesn't have the. I think it wouldn't have the features. So there is this feature that let's say the strongly coupled strings have of wanting to pull the tip back to the boundary. I think they will not have that feature.
Right.
The tip will want to fall into the black hole or to move to the infrared. In fact, in n equal to 4 super young mills, we expect a transition for the adjoint representation. As we make the coupling smaller and smaller, at some point the tip of the string will want to go to infinity.
I think we wrote a paper on this, right?
Yeah. One of your papers.
A little bit tangent to the main discussion, but related to that, and also related to engaged BFSS model. You and Milekhin are emphasizing that it may be useful for quantum computing because gauge singlet constraint, imposing gauge singlet constraint on quantum computer may be very difficult. You're commenting that it seems that people who are trying to construct a lattice gauge theory for quantum computer, they are struggling with gauge singlet constraint. Projecting Hilbert space to gauge singlet is very hard in general. And I wonder how generically this kind of ungauged theory can make sense, because probably if people can construct a lattice gauge theory on quantum computer, it's probably ungauged version. And except for BFSS or supersymmetric theory, this kind of ungauge theory can make sense, or?
Yeah, I haven't thought about the higher dimensional lattice gauge theory, whether it makes sense. I mean, just as a general principle, I think it might be that you would like to simulate some system where it's not the lattice gauge theory, but it's something else where the gauge fields are emergent and we're not. I think that's a philosophy that might.
Right. The condensed matter people hope that there are ungauge systems that somehow at lower energies behave like gauge systems, right? That's
yeah, but
they say in some models.
Yeah, but I just thought if we can directly use just ungauge lattice, it's more straightforward. I mean, it's easier to construct.
Yeah. But the simplest for the theorist might not be simplest for building in a quantum computer.
Okay.
Or building in a quantum simulator. So.
Okay.
I mean, it might be an opportunity for theorists to figure out how to get the gauge fields from various systems, simplest possible systems.
I guess CPN model is usually mentioned, right?
Right.
It's emergent gauge field. I always get confused in thinking about this.
I'm unaware of this work on the ungauged BFSS model. Is there some understanding of what the gap is between the singlets and the non-singlets?
Yeah, there are some indirect arguments. Well, there are some analytic arguments that it is lambda to the 1/3. And then there is a numerical simulation that Masanori and friends did that kind of confirmed that. Well, within some, I don't know whether that's what you would say. But.
Okay, interesting.
All right, are there any more questions?
I would say that, yeah, I just had a comment about what Emil said a moment, sometime before. I mean, I'm not sure that the black hole will be, but there will be a black hole, because in this, I kind of share a bit Emil's concern that in this matrix model, many times in the past, we thought, oh, maybe this will lead to a black hole. And in the end, after you analyze it enough, it just happens that the string theory behaves weirdly. And in the end, it's not anything close to a black hole. And so this is just another one. In this case, we cannot solve it, but maybe it will be found that you can actually solve all this non-singlets and so on, and it doesn't behave like a black hole. I mean, that's certainly a possibility.
Well, the KKK model was based, I mean, the claim that it's a black hole was based on a particular calculation. You remember, on the one hand, it's FCZ duality to Sine-Liouville model. On the other hand, perfect coincidence with the partition functions on two sides, yes?
Well, the way I interpret your calculation is that the entropy looks like is that of a black hole. I mean, you solve the background, but it's not obvious that the object that you're finding is a black hole. So the evidence that it looks a bit like a black hole is the entropy. I don't think there is any further evidence in that.
No, analytically, of course, it was this calculation of Greg Moore, which was done from Liouville theory, Sine-Liouville theory, let's say, and then we found a very non-trivial coincidence with the partition function.
Okay, sorry. No, I'm not claiming it doesn't give the SL2O module 1 background. I'm just saying what type of black hole behavior, just by analyzing physical whether it's right to call it a black hole. So because Emil raised the possibility that even though it looks like geometrically a black hole, in the end, it will not behave like a black hole. And behaving like a black hole, it means having certain properties, like I would say having an entropy that goes like 1/g string squared, having scrambling information,
of course, all these
thermalizing, and those properties. So I think out of this list of properties, you check the entropy property. That's what I meant to say. Of course, you demonstrated pretty well that this that what you calculated describes the SL2 module 1 background.
No, not only this, but this is a sign-Liouville theory. Well, that's what we demonstrated.
Right, but
yeah.
in the regime where there is the FZZ duality, and you're in the string black hole phase diagram, you're in the regime where the string description is the more weakly coupled one. So in the FZZ duality, the sign-Liouville is the more weakly coupled description of the dynamics than the black hole is. And whenever we have a strong weak coupling duality, we always think that that the weakly coupled description is the one that describes the effective dynamics the most correctly. And so if the sign-Liouville is the most weakly coupled one, then the physics should be that of string condensates, not of black holes.
I mean, duality is duality. It's just for any couplings. It's dual models, and we describe for all couplings the sign-Liouville. Right,
but if your intuition about it's behaving like a black hole is coming from some kind of effective field theory notion of what black holes look like using the gravity action to do calculations of the dynamics around this background, then you're using the strongly coupled description, where a weakly coupled description in the dual theory is more accurate as to what's going on.
Sorry, Emil, but
sorry, Emil, but I don't think that's quite a fair objection, because the string condensate and the sign-Liouville is T-dual. So we're still talking about a winding mode condensate, and that's still not, that's still very much black hole-like, because
right. So we're arguing about the physics in Euclidean signature, and then there's a whole can of worms as to how to think about that in Lorentzian signature. But there's been this intuition going back to the very early days, in the 80s, that the winding condensate, going back to Attic and Witten, basically, that the winding condensate is telling you about Hagedorn physics of long strings. My understanding of what the winding condensate is in the sign-Liouville is that in Lorentz signature, it's precisely describing a gas of these long strings.
But Emil, can I ask a simple question? If we are able to change the radius, aren't we guaranteed that for some regime parameter, we will get something that is more close to black hole and has black hole features? I mean, if we cannot change the radius, I agree. We are close. If we're on the wrong side of the correspondence point, then okay. But
well, there's no reason why you shouldn't be able to change the gas of the temperature of a gas of these long strings.
Right. So then you need a model that contains a phase transition, right, or something like that.
Yeah, I guess if there was some sort of a phase transition in the model, but I mean, but Volodya and his collaborators worked out the partition function, and there's no discontinuity in the free energy at beta equals 3/2.
Well, for that particular model, yes.
Yeah.
What would be an order parameter for a black hole? I assume you need a dynamical order parameter. Is it quasi-normal mode? Is it exponential decay in time? Can someone mention at least a quantitative feature? Is it exponential decay in time of some dynamical process, like a quasi-normal mode or something? Is that something?
Yeah, I think so. I think you study the close string scattering in the cigar and in the Lorentzian cigar background by continuing the results from the Euclidean calculation. You will find that.
Would you consider that a black hole, Emil, if it has quasi-normal mode behavior or exponential decay in time in the Lorentzian picture?
I mean, you can have
mode is just an indication.
We should at least agree on the order parameter.
Well, but so there is this Hagedorn gas of strings, right? So you send in a probe, it can get absorbed by this Hagedorn gas of strings.
I think
How would I distinguish? How would I distinguish
the dual
being absorbed by a big heavy string from something that's a quasi-normal mode of a black hole?
You're worried it might be like a fuzzball or something that looks a lot like, even dynamically, might look like a black hole, even though it doesn't have.
Yeah, you've got this gas. There's nothing about it that looks particularly black hole-like, right? You've got this gas of long strings that loop in from infinity, and there's nothing that looks like a horizon or closed trap surfaces or any of the things that we usually associate with black holes. Furthermore, the mass of the black hole can't be adjusted. It's this parameter mu, which is a non-normalizable coupling. So it's something that's like fixed once and for all.
So I have a question. So Juan mentioned scrambling, and so besides the quasi-normal modes, did people compute like tachyon 4-point functions or something that one could probe the scattering near the horizon to see like what is the Lyapunov, if it's to see there is a more, how the would-be horizon behaves a little. Maybe that would be a better probe, I guess. I don't know if people studied it.
I guess it's a question to Balthazar, but I guess like from the matrix model side, it's hard, right? Do you agree, Balthazar? Because like we are scattering momentum modes in the presence of winding modes.
Mm-hmm.
And that is why like a Balthazar proposed like a. Sorry, yeah, go ahead. Yeah, this is why Balthazar proposed
Balthazar proposed a method for computing the 2-point function. Yeah. In principle, the same method carried further could give you the 4-point function.
Yeah.
And then a little more, and you get the out-of-time order 4-point function.
Right, but I should mention that. Sorry. Yeah. Sorry. Go ahead.
No, just a quick question. This, if you can compute it from the Cosset CFT perspective, I guess from a
that would be good. Yeah, I don't know whether that I don't think that was done. But.
By the way, there was a paper. I mean, already in the paper, in FZZ paper, there was a calculation of mixed correlators, both vortex and vertex correlators, but not all of them. And I remember there was a paper a few years after, and already quite a time ago, where all the correlators have been computed, mixed correlators. Maybe one could undig this paper and really try to do the calculation a la Greg Moore, but including already a couple of momentum modes. I mean, computing.
Winding modes. Yeah, I think in the matrix model, the mixed correlators have not been computed, right? As far as
at the level of the 2-point function, if you're looking for quasi-normal modes, I mean, the 2-point function is known, right? It's just this standard ratio of gamma functions that you get in all of these models.
Mm-hmm. Yeah, but the Lyapunov is a little bit more fine-grained. I don't know how to say it. Could imagine that you have a system with a quasi-normal modes, but still there is without the...
Yeah, I just wanted to confirm first whether there were even quasi-normal mode behavior, but this seems to be confirmed or not.
I'd have to look. I don't remember off the top of my head. I mean, it's a question of what's the physical interpretation of all the poles in the gamma functions. Juan, do you know?
I don't know. I don't know what the answer is.
Emil, do your objections hold for the BFSS model?
No. No, they're one. I mean, they're the so whether one is on the black hole or the string side of the correspondence line is a question of what's the curvature in string units. So in BFSS, as long as your black hole doesn't have size, n to the 1/3, it's a standard black hole in supergravity, and the curvature is small in string units at the horizon. So here, this black hole in these 2D models The fact that the linear dilaton is large mean in string units, the slope of the linear dilaton is greater than 1 in string units, means that the curvature of the black hole is greater than 1 in string units. And so that's the indication that you're on the string side of the string black hole phase transition. I think the fact that the strings are going out to infinity and not trying to attach to something at r equals 0 is also an indication that you're on the string side of the black hole string phase transition. That
here they have to go to infinity, right?
Yeah, they have to go to infinity, and that's because
I thought that's
the D branes in the matrix model are continuously cycling in from infinity. They can't sit there stuck at the origin and make some kind of bound state, which is our usual interpretation of black holes in string theory. So the fact that the D branes just come into this, you know, quadratic barrier and reflect back out without staying there for a long period of time is also an indication that you're not forming something you would conventionally call a black hole as we know it from
how do you know that in a non-trivial representation you don't get stuck near the middle? Because
that's a very good question. I tried for some time to try to understand what the eigenvalue dynamics is in the presence of this Calogero correction. And I think that's maybe a fruitful place to look and see, can eigenvalues get stuck in the presence of that coupling? That's a very interesting question.
By the way, Spenta is raising hand, so I guess.
Juan, firstly, thank you for a very fantastic talk. Actually, I really appreciated your insights into this long-standing problem. I have just some suggestion because when you wrote down the Calogero model, there was a spin-spin interaction, which was the centrifugal part of the Calogero Hamiltonian, this pi r upon lambda I minus lambda j square. Somehow it reminded me of the old SYK model, which has spin-spin interactions, which then you randomize them, and then you introduced the representation of the spins in terms of real fermions, and you had this all-to-all interactions, which somehow gave rise to a very complicated chaotic type of dynamics, which is somehow characteristic of what you expect from a black hole in a matrix model. So I was wondering whether if we modify this matrix model written out in this Calogero form and using random spin interaction type of idea, it's changing the model, but it might actually have all the complexities to give rise to a non-integrable system. I just wanted to make that point. Actually.
Yes, that sounds interesting.
Did anyone have any more comments? Okay, perhaps we should take a 5-minute break and then Bruno will speak. Does that sound good?
Sounds good.
All right.
Yeah, that's good.
Do we need a break?
What'd you say?
Do we need a break?
Yeah, 5-minute break.
Okay.
4 minutes now.
All right.
Stretch your legs, go for a walk.
Well, yeah.
Make yourself a cup of coffee.
Oh,
compute the quasi-normal modes of the 2D black hole.
In the next 5 minutes.
Now I have to go. It's 1:20 p.m. 1:20 a.m. here.
Good night, Masanori, and thank you for joining.
Yeah, bye-bye.
By the way, about the quasi-normal modes, there was a paper by Schafferis a couple of months ago comparing the exact 2-point function in some limit to to a semi-classical calculation of the string propagating in the black hole background. I don't know if you reproduce. It sounds like that might be helpful.
Yeah, Emil said some reference about some gamma functions, but that sounds like there is, if they have complex poles, it sounds like they're there. Mm-hmm. But I don't know which reference he was talking about. Some maybe from the older literature.
Dio, I think there are some recent papers by a group in Israel by Itzhaki and Givion. They wrote a series of papers on 2D black hole, and so
okay, yeah. It's the simplest dynamical question you can ask, whether there's quasi-normal mode behavior. It's not the definition of a black hole, but it's the first thing you should verify, I guess.
Yeah, they wrote a series of papers that have this function, the gamma function, you know, formulas in it, and it's like a series of papers.
I'll take a look then.
Look. Yeah.
These are these Givion Itzhaki papers?
Yeah.
Okay.
Also, does anyone know if the FZZ paper is always cited as unpublished, is available somewhere online?
I've not seen it.
Yes, Volodya is not here.
But it's there, you say?
No, he's not here.
Oh.
Because he's the person to ask.
Maybe we can put it on the Slack.
Yeah, exactly.
Yeah, I was going to do that.
Let's put it on the Slack.
I did it. I put it already.
You asked the question.
Available in any form, and someone has it and can scan it.
I meant putting the paper on the Slack,
yeah,
not the question.
Dio was suggesting someone put the paper on the Slack.
Well, I asked the question. If somebody has it, maybe they can.
I don't even know if there's a manuscript of a paper.
Oh, really?
But Volodya would know.
Yeah, Dio, isn't this ratio of gamma functions even in the new hat paper? That they can...
Well, you should ask Emil, I guess, but I didn't think they were doing black hole calculations in that paper, or cigar calculations there.
Well, I mean in the matrix model.
I don't know.
That's the thing that's in there would be the S matrix in the standard Leibel background, not in the sine Leibel background.
Yeah, I don't expect any quasi-normal modes in that thing.
Okay, can I start?
Yeah, go ahead.
Okay, yeah. Thanks for the organizers for putting together this wonderful conference, and thanks for the opportunity to speak. So I'll be talking about a similar topic to what Juan just told us about long strings, non-singlets, and the two-dimensional black hole in sequels on string theory. So one of the reasons why we want to focus on sequels on string theory is because it's a nice toy model where we can explore a lot of features of the worldsheet formalism that we can hope to apply to perhaps other more interesting models. And another reason is because it has a dual description as a UN matrix quantum mechanics. And for example, this matrix quantum mechanics, a lot is known about the singlet sector states and their relation to closed strings. And this has provided numerous insights, for example, in the new developments in the instantone's contribution to the worldsheet formalism that were discussed yesterday. And so we can try to use this matrix model to learn new things about the worldsheet of C equals 1. And in particular today, we're going to focus on non-singlet sectors and their connection to Sine-Liouville theory. Okay, so the first part that I want to focus on, Juan already introduced a lot of these concepts, is the relation between non-singlet sectors and the long strings in C equals 1. So this is based on his paper in 2005, where long strings are essentially open strings or some very energetic open strings on G1 branes. And I want to focus on some of the computations that you can do to check this duality, such as the computation of tree-level scattering amplitudes, based on this work a couple of years ago with my collaborators, Victor Rodriguez and Sheehan. So this part is going to be similar to Juan's discussion in C equals 1. And then I want to focus on another topic that he mentioned, which is this, now it's in the Euclidean setup, where you consider the closed string background at finite temperature, and you're going to essentially introduce a thermal ensemble of long strings. So we introduce now worldsheets that have holes. And in a particular tooth-like limit, you're going to be able to essentially close up these holes and replace them by a background deformation, where the deformation is just the Sine-Liouville potential as you'd expect. So this is purely a worldsheet description, and it'd be nice to, I'm going to describe some of the computations. This is again based on perhaps a more hidden section of the 2005 paper by Juan, and also some work in progress with my collaborators. Okay, but let's start by describing long strings in C equals 1. So, okay, this has been reviewed a number of times in this workshop already, but the worldsheet formalism consists of a time-like free boson together with the C equals 25 Liouville CFT, which is the spatial direction. So the picture is that you have this Liouville wall over here, and you also have a exponentially growing string coupling, such that in the asymptotic region of large negative phi, you have a continuum of states. In particular, you have incoming and outgoing closed strings. So they come from infinity, they reach here near the region near the Liouville wall, where the string coupling is finite. There they can interact, and then they reflect back and go out. And the vertex operators for these closed strings can be written in the usual worldsheet formalism by combining a vertex operator for the free boson together with a vertex operator for the Liouville scalar primary. It will also be interesting for us to consider boundary conditions. So yesterday, the ZZ boundary conditions played a key role in the instantone discussions. So today we're going to talk about the FZT boundary condition. So this comes labeled by a parameter S. Okay, and we form the FZT brane by essentially extending this in the time direction. So the picture, it's convenient to have a semi-classical picture of what's going on. It's convenient to look at the action, and in particular, you focus on this term, which is a boundary potential, and the coefficient is essentially related to the parameter S. So the picture is that, for large negative values of phi in the asymptotic region, you just have a continuum of open strings that move freely because the potential is essentially zero there. And then at some point, as it reaches a value of phi that's near minus s, the ends of the open string feel this potential and they get stuck there. And so the open string reflects back. So this is kind of like a D1 brane that ends in space. So it's like a semi-infinite D1 brane. Okay. And then you can go on and compute the vertex operators for these open strings. You can introduce some Champeyton factors, which correspond to different FZT parameters. And once you combine the Liouville boundary primary operator together with the free boson, you form the usual open string vertex operators. I should also say that the boundary structure constants are known explicitly, thanks to the works of these gentlemen. And so they're explicitly known. There's some nasty expressions, but they're known. So in principle, you can just go on and compute any boundary correlation function, the Liouville CFT that you'd want. And we're going to do that soon. Okay, it was also discussed in this conference a couple of days ago about, and it might be discussed this afternoon actually, about the dual of FZT brane. And for generic values of the parameter S, I think it's still an open question. So what we do know, however, is the so-called long string limit of an open string on the FZT brane. So for that, we consider a vertex operator for an open string, has energy omega attached to an FZT of parameter S here. And we consider the limit when we send omega to infinity. We also send S to infinity. And we keep the renormalized energy epsilon, which is omega minus 2S, finite in this limit. So the interpretation is that the subtraction by minus 2S is like subtracting the energy of the long string that is due to the string tension. Okay, so it's like an infinite contribution. And the picture is that, if you have an open string of finite energy, these are going to decouple from the bulk because they're going to be localized on the FZT brane that moved off to infinity, where the string coupling vanishes. But the long strings, which have infinite energy, they're going to move towards the end of the FZT brane. Then the ends are going to get stuck here, but the tip of the long string is going to keep moving. Okay, so that was the picture that Juan also drew earlier. So there's a potential due to the string tension, but provided it has enough energy, it can overcome this potential and essentially reach the bulk of the theory where the string coupling is finite. And then once it reaches here, at some point it starts retracting back, and then it goes back out to the FZT brane, to the asymptotic region. Okay, and turns out we can go on and compute some scattering amplitudes of such long strings. So these are well defined. So for example, let's consider the tree level long going to long plus closed scattering amplitude. So this consists in the in state consists of a long string that's just moving towards the bulk. And then at some point, the tip of this long string is going to pinch off, and it produces a closed string together with another long string, and both of them move back out to the asymptotic region. The worldsheet diagram that's relevant for this computation consists of a disk diagram with a closed string insertion and two open string insertions for energies omega. This disk diagram, you compute them by decomposing, inserting a complete basis of open string states, and then you write it in terms of the bulk boundary structure constant and the boundary 3-point function on the disk. So both of these are known, and then you also have to multiply by the appropriate conformal block, which is just the sphere conformal block. You integrate over the Liouville momentum. And you also have to do the integral over the position of one of these boundary vertex operators. So doing that, you find the result for the scattering amplitude of an open to open plus closed amplitude. But what we're interested in is in the long string limit. So essentially this computation that I described gives you one of these points here. So then you do this computation for another value of S that's higher and you get another point. And you keep going like this while keeping epsilon, the renormalized energy finite, to extract the final value for the long to long plus close scattering amplitude, which is given by this red result here, which is just the asymptotic value. So that's the result that you get for a single point in this diagram on the right. And then you do this for as many points as you want. And from that, you read off the long to long plus close scattering amplitude of long strings. Okay, so we have some semi-classical understanding of this scattering amplitudes in some regimes, but we don't have an analytic expression. So instead, what we're going to do is we're going to see that we can also reproduce the scattering amplitudes from the matrix model side, which I'm going to describe next. Okay, on the matrix model side, you start with the usual Hamiltonian for a matrix X with the inverted quadratic potential. You do this rewriting in terms of the diagonal, in terms of the eigenvalues and some angular components, and you arrive at the usual Hamiltonian in terms of the eigenvalues times some plus the contribution that now appears for non-singlet sectors. And the sector that's relevant for n long strings is going to correspond to n copies of the adjoint representation. Okay, but let's start small. Let's revisit first the usual singlet sector. So there you only have the Hamiltonian for the eigenvalues, which are just non-interacting. And they're at a chemical potential minus mu. So the ground state just consists of filling up, for example, one side of this inverted quadratic potential up to the energy minus mu. So I'm only going to talk about perturbative effects. So I don't care about what happens on the other side of the potential. And the usual picture is that fluctuations of this fermion density, of this Fermi C, they move towards the potential and then they reflect again. So this is the same as closed strings. And the parameter mu is related to the string coupling in this way. Okay, this is the usual picture from which you can compute the scattering amplitudes of closed strings on both the matrix model and on the C equals 1 side. Okay, let's move on to the adjoint sector. And now the adjoint sector state can be written in this form here. So just a couple of comments. So this wave function psi 0 of the eigenvalues consists of the singlet sector ground state wave function. So that's the configuration where you fill the one side of the inverted quadratic potential that I drew here on the right. The IIs correspond to the 0-8 states of the adjoint sector. And the fact that you have to restrict to 0-8 comes from the fact that, when I did this decomposition, there is some residual ambiguity that essentially constrains you to only choose states that are 0-8 states. And finally, perhaps the most important piece is this coefficient here, which is a function of a single eigenvalue, lambda I. And the interpretation of this is that this is the wave function for the tip of the long string. Okay, so the picture is that you have this Fermi C that's filled, and then you have a particle that's sitting somewhere here, and this particle moves towards the potential and reflects back, but it's moving under a different dynamic. It has a different Hamiltonian. Okay, so you can take the Hamiltonian we found above and act on the state W, and the usual part that only has the eigenvalues, non-interacting, you just get the ground state wave function here, plus some terms that are suppressed in the weak coupling regime. The new term is the non-singlet term, and this can also be expanded in 1/mu. And the leading term is what we call the free Hamiltonian for the long string. So the proposal by Juan in 2005 is that the long string eigenenergy equation is essentially the Hamiltonian problem given by this Hamiltonian that you find from the non-singlet sector contribution. But this Hamiltonian suffers from an IR divergence, which is to be expected because the long string on the worldsheet, okay, as the name says, it's a long string, so it has an infinite energy. So you need to subtract the tension energy of this long string, which it's straightforward to do. And once you do that, you arrive at a completely regular Hamiltonian, from which you can extract the wave functions WE of lambda. So these are the wave functions for the tip of the long string. And in fact, this can be solved exactly, and this was done a couple of months after by Fitkowski. Okay, so this is very nice because now we have a Hamiltonian for the long string. We have the wave functions exactly. So we can, it's a quantum mechanical system. We can essentially compute anything we want.
I can ask just a simple question.
Yeah.
This IR divergence comes from this truncation and the onsets that you take for the wave function. Like the full theory doesn't have this IR divergence.
The IR divergence comes from essentially this interaction here between the eigenvalues. Once you take the continuum limit, it's just there. Yeah, it's due to the interaction between the eigenvalues.
I mean, if you had the exact matrix model deal with FTD brane at finite distance, then you would not have this divergence. But this matrix model is already the S goes to infinity limit. So the divergence is there, but there's still meaningful comparisons to the worldsheet code.
Yeah.
Yeah, or finite n matrix model would not have divergence. It's just that you took the double scaling limit.
Right. It's only in the infinite n limit, yes. Or in the continuum limit, essentially. Okay. Okay, good.
I think it's both infinite n and when you send the Fermi level to the top of the potential, right?
Can you say that again? Sorry.
Yeah, the divergence appears when you send the Fermi level to the top of the potential. Like just infinite n. I mean, it appears in the double scaling limit only. Right?
I mean, strictly speaking, we're talking about different kinds of divergence here. I mean, this divergence would be cured even if n is strictly infinity, provided that we, instead of saying we relax the non-singlets factor, we add this fundamental matter. You can treat that correctly, which corresponds to having FTD brane at some finite distance. I mean, this divergence we're talking about is because FTD brane retracts off infinity. That's the source of it.
Yeah, if you just look at the non-singlet wave function and just the basic matrix model, right? I think that the log divergence appears as you send the Fermi level to the top of the potential. At least.
Right, in the double scaling limit, right?
Yeah, yeah.
Yeah, I agree with that. So yeah, so it's like when you, okay.
But the divergence that's being discussed here is not actually, I would not say due to double scaling limits because, if you had the actual matrix model deal to FTD brane at finite distance, there would be no long string energy divergence. Then long string energy would have been finite. It's just that in that case, the non-single sector is introduced through the coupling to the fundamental fermion.
Yeah,
which is
I'm talking about just the original model without the fundamentals. And when, I mean, it's the calculation that Gross and I did, where we took the Marquezine-Onofre equation. And I think only when we continued it to, when we double scaled it, then we obtained this log divergence in the adjoint energy level. Well, we can talk about it. I'm just talking about the original matrix model where you have the singlet sector, and then if you look at the lowest adjoint sector, I think you need to scale the Fermi level to.
Yeah,
well,
so
the
quartic model. Yeah, in the quartic model, the the energy goes like lambda to the 1/3. I mean, this is what Marquezine and Onofre found.
Right, right. For positive.
That would be a limit that goes to infinity, as you correctly say, as you say, and notice. So.
Okay, just yeah. What she was saying, by the way, in case people didn't follow, is that if you consider FCT brane a finite S, you can scatter open strings on this FCT brane. And then there we see no divergence because S is finite. So the divergence only appears when you send S to infinity. So if you had the matrix model dual of such an FCT brane, you wouldn't expect that to have the same divergence. Okay. Good. Yeah, okay, so let me discuss now the scattering.
I have a very simplistic question. In what remains of the target space picture, if there is any, is there some observable that measures the number of FCCT branes asymptotically? Something like Ramon charge in string. Is there some analog of that in this case that measures the number of FCCT branes?
Not that I'm aware of.
From what point of view? Are you talking about from the worldsheet or from the matrix model?
I thought you were talking about from the worldsheet.
I mean, the brane is sitting there. I mean, why do we need some other?
Is it just the energy? Yeah. So what charge do these things carry? Any charges aside from energy? Any discrete symmetries or anything like that, or is it just? I typically have a picture of branes carrying gauge, some sort of, but maybe it's just not applicable.
Theo, I think maybe you are asking what is the back reaction on the closed strings. Is that what the question is? Because I mean, the branes are there, they support open strings. They are literally sitting there in space. So why do you want to have some alternative way to detect the brane? Maybe you're asking what is the back reaction on closed strings.
But can I ask something? There could be a gauge field living on the FCCT brane, right? And then it could sort some flux.
The FCCT brane has a cosmological constant term, which when excited gets rid of the FCCT brane. So I don't think it can have any conserved quantity.
Good, so there's no such thing really as the number of FCCT branes.
Sure there is.
No, there is because in weak
open string.
Because we have some weak coupling.
If you have 3 FCCT branes, you have 9 different species of open strings.
Mm-hmm. Right, there is an NF, but.
Yes, okay. So you read it off from the yeah.
It just seems I'm confused. Anyways, sorry about that.
No. I mean, but it is a D0 brane. So in type 0b, won't there be a discontinuity in the Ramon potential? Depending on whether I'm inside or outside the FCCT brane? I mean, it's close string description, right? I thought the interpretation is it's something that comes in and goes back out. Or am I misunderstanding? It's a D0 brane, right?
E1, the FCCT.
G1, yeah.
That's why.
Yeah, no, then, right, there's no inside or outside. Yeah, sorry.
Okay.
Well, maybe one point to mention is that, you know, this extends to infinity, and at infinity, the string coupling goes to 0. So you know, because asymptotically it becomes a free string theory, you can just count the brain. There's no ambiguity of, you know, due to any kind of interaction that, you know, the number can be ambiguous. There's no such thing here.
Good. I like that. Okay, thank you.
Yeah, thank you. Okay, so now we can go on and actually compute, because we have the, you know, we have the matrix model, we have the wave functions. You can essentially go on and just compute anything you want in this quantum mechanics problem. So the simplest thing you can do is compute scattering amplitudes in the Born approximation. So this would be like 3-level scattering amplitudes. So all you have to do is put the, you know, take the matrix element between the incoming long string. This is for the long to long plus closed scattering. And the out state is a long string together with a closed string, where the interaction Hamiltonian is just H minus the Hamiltonian for the free long string. And turns out that once you do that, it's a lot simpler than the worldsheet, and, you know, it's a completely different description as expected from this duality, but the results exactly match. Okay. So in this way, you know, there's a very direct map between this Lorentzian observables, which are these long string scattering amplitudes on the C equals 1 side and on the dual matrix quantum mechanics. So that's very nice because, you know, it provides a Lorentzian description of these non-singlet sectors. But actually for the remaining of this talk, I actually want to talk about the Euclidean setup, which is related to this closed string background deformation. So now the setup is the following. We're going to consider C equals 1 at finite temperature. So we have a Euclidean free boson that's compact on the radius r, plus the usual C equals 25 Liouville CFT. Oops. Okay, so let's start with the string theory side. We want to include long strings. So we're going to consider NF FZT boundaries. So again, the number of FZT enters here. So the partition function just consists of exponentiating all empty diagrams. So the empty diagrams without boundaries, these correspond to the usual diagrams that give you the thermal ensemble of closed strings. And then you have other diagrams with boundaries. For example, you have the cylinder, which is order GS to the 0. You can have the cylinder with a handle, which is order GS squared. Or you can have the sphere plus ... or the sphere with the 4 holes, which is also order GS squared, and other diagrams with more holes. So let's start with the simplest computation, which is just a cylinder with no handles. So, you know, you can think of the cylinder as having 2 FZT branes that are exchanging a closed string. So you get a factor of NF squared for each FZT brane. And then you sum over all the exchanged closed strings. So you have a sum over winding and an integral over the Liouville momentum. You have the coupling to each FZT brane. And finally, you have a factor due to the propagator. Okay. So now, okay, there.
Bruno?
One caveat is, yeah.
Do these carry all the same FCZT parameters?
Yeah, sorry. Here I'm considering them all to be at the same S.
Okay, thanks.
Yeah. Okay, so now what I want to do is essentially deform the P contour to the upper half plane and pick up the poles. So there are poles at P equals 0, and there are 2 kinds. One of them is the ones that have non-zero winding, and these are a specific feature of the cylinder diagram. So they can be understood from the matrix model side as well, that we'll see later. So I'm going to neglect those. And the other kinds are the zero winding and p going to zero poles. And okay, I'll ignore them for now, but I'll come back to them soon. So
Bruno,
if you ignore, yeah.
Sorry, because we had done this computation also with Olga in our paper, actually you can pick any poles, any winding, right? Not only focus on plus minus one in this computation.
Oh yeah, yeah. But the others are suppressed in the large. Sorry.
In the largest limit, yes, they're suppressed. Okay.
Yeah. So I'm going to restrict to. I'm interested in taking the long string limit. So S is large. So I'm going to focus. The ones that dominate are the winding plus or minus one poles, provided I restrict R to be between 0 and 1. And turns out that the constraint that R is between 0 and 1 is specific to the cylinder diagram, because it essentially comes from the fact that there's a pole from the cinch of the FZT brain here that dominates if I go above 1. But if you have other diagrams, there's actually a 0 from the sphere 3 point that cancels this pole. So I can go all the way up to 2. Okay, so like Panos was saying, in general, you have to do this whole sum. It's not just the plus or minus winding equals 1 poles. But now I want to take the tooth limit, in which I sent the number of FZT brains to infinity, while also sending S to infinity and keeping this parameter lambda fixed. Okay, so then clearly only the plus or minus winding 1 poles dominate. And now the picture is that the only contribution you have is this residue contribution from this Liouville momentum continued and the plus or minus winding 1 poles, which is just a sine Liouville deformation. Okay, so the interpretation is that you're just deforming the closed string background with the parameter lambda by the sine Liouville potential. So you arrive at this picture that I drew at the start. Okay, and so by tuning this parameter lambda, you can start at C equals 1 string theory at finite temperature between 0 and 2. And then as you increase it, you eventually arrive at the sine Liouville theory. Okay, so again, on one side, you have the thermal ensemble of long strings. And on the other side, you have sine Liouville, or maybe I should say C equals 1 deformed by sine Liouville.
So Bruno, is it correct to say that you basically integrate out the open strings and get the backgrounds for closed strings only?
I think that's what I'm saying. Yes.
Yeah, I mean, yeah, or more precisely, you basically solve for the open closed string field equations of motions to get the closed string background. I guess maybe that's a more appropriate way to put it.
Yeah, I think in terms of the
Bruno didn't quite give the general argument. It's just demonstrating the simple example. But
the general the general argument is the same, because all that matters is that you have this is the coupling of the FZT brain, the propagator. That's essentially it, and then you can just deform the contour.
Thanks.
And I guess implicitly, because you're doing this in worldsheet perturbation theory, lambda is asymptotically smaller than, is sort of like as much smaller than mu as you want it to be. Mu is asymptotically larger than lambda.
Initially I'm thinking of lambda as being infinitesimal, and then in some sense I think of doing this to all orders and then resum, and then I can tune lambda to whatever I want to arrive at the sine Liouville theory. But yeah, at the start, lambda is infinitesimally small.
I'm just wondering, so if I really wanted to do that, I would need to also resum the mu 1 over mu perturbation series. If I really, I can't just turn.
I think you can do it.
I can't just turn mu off, for instance, right?
There's a double expansion here. So even though in the formula for lambda that Bruno wrote, the G string is included, there's a separate expansion in GS and in lambda. So we can talk about the given order in GS and given order in lambda. So because the parts that tend to infinity are just NF and S, the G string could be finite, or 1 over mu.
Yeah. So yeah, so in this formula, yeah, the things that go to infinity are in F, and I guess here, in F and S. GS could be anything.
Right. I'm just wondering about the domain of applicability. So it's I agree. You're resumming the lambda series, but working at some fixed order in G string. So.
Yeah, so in practice, what we
like
do,
you're working at, that 1 over mu is somehow being held to be very large in order that you could work order by order in G string.
Sorry, what do you mean by the mu? I mean, mu is just 1 over G string.
Yeah.
What did you?
Right. So in the matrix model, that's codes mu. The height of the Fermi sea.
Right.
Yeah. So GS. Yeah. Okay.
Right. So I'm just.
So I mean, from both on the worksheet and on the matrix model side, we can work at a given order in the semi-classical expansion. So either in G string or in 1 over mu. And then we can, at the given order, we can talk about the expansion lambda and summing up the expansion lambda at that given order. So for example, the strong lambda, large lambda, you expect to get to the black hole and or the tiny reveal. And we should be able to talk about string perturbation theory in that background as an expansion in 1 over mu.
Right, but so like the sine-Liouville theory is a theory where you have the winding perturbation turned on and the usual Liouville tachyon perturbation turned off. The calculation that's being done here is a calculation in the presence of the ordinary tachyon condensate of a small amount of sine-Liouville coupling turned on in addition. So I'm just wondering if there's some subtlety associated with that because it's being done in a theory where you've taken the biggest coupling in the theory to be the usual Liouville tachyon background. So you get in the end of the day something which is the I suspect it's something that's perturbative in lambda over mu.
No, we can talk about perturbation theory and lambda and 1 over mu independently. I mean, here it's true that both Liouville potential and sine-Liouville, CDO sine-Liouville are turned on. And the expectation is that when you take if you can take lambda to infinite limit, if you can sum up this series just in lambda and given, say, a leading order in GS, then the sine-Liouville dominates over the Liouville, and you can throw away the Liouville, and you end up with the sine-Liouville, which is TDO to the black hole.
Right. So how do I know there aren't some effects that are large when mu gets small that don't overwhelm the things that you've computed?
Well, but mu is always kept large here, right? We're never taking mu to be small.
Right.
Yeah. So in other words, you can always ignore.
You can compensate for you can compensate for that by the largeness of NF. So maybe the question was, how do you make lambda finite if GS is small? But here you have this NF and e to the minus 2 pi RS. You can make NF huge to compensate for that.
Yeah. So we usually do a string expansion in GS and also an expansion in lambda. So you have these two expansions.
All right. I think I understand what's going on. All right. Thanks.
Yeah. Okay. So yeah. So the picture, like Emil was saying, is that you start with C equals 1, and then as you tune lambda, you can arrive at the sine-Liouville theory, provided you can sum this up. But in practice, what we do is just sort of conform a perturbation theory around this with this background deformation. Okay, I also wanted to say briefly that the zero winding and P going to zero pole, it also corresponds to a background deformation, but it's a background deformation by essentially the VEV of the dilaton. So essentially it corresponds to shifting by the Liouville potential by some infinite amount. but that can just be absorbed in a shift of the field phi, which is just a shift of the dilaton value. So it's a renormalization of the string couple. Okay, and
sorry, can I ask a
cool.
question?
Now I can describe. Yeah.
So this peak was 0 pole. So originally it's right on top of the contour, right? So is there any like a prescription or like a natural argument how to avoid it?
Yeah, so I guess these arguments so far are a bit, if you were to write all the formal expressions for any of these diagrams, they always run on top of this contour.
Right.
So what I'm saying here is that you just absorb the pole that you get here. So you choose some contour prescription, and the contribution from this pole you just absorb in the renormalization of the string couple.
I see. So you can use like whatever contour you want, but it can always be absorbed by the renormalization of the couple.
Yeah, that's right. So this is maybe I should say this is the Fischler-Susskind mechanism.
Right.
Maybe another way to say this is just that to define what we mean by precisely by putting FDD brain in the C=1 background requires this choice of contour. Otherwise, you end up with some divergence, an infrared divergence.
Maybe there's some more rigorous way of doing this, but I think at the level of the rigor that these arguments go, I think this is not the most worrying step. Okay, so now I can describe some actual calculation that you can do to test this proposal. So first, we're going to go to the matrix model side right after, but let me first describe the worldsheet side. So again, the contribution from in the computation of the partition function, the contribution from the closed diagrams give you the closed string thermal ensemble. And then you have from the diagrams with two holes, they're here, are the contributions that go as NF squared. And then you have a contribution that's order 1, and then GS squared plus ... Okay. The sphere with 4 holes goes as NF to the 4th times GS squared. So the contribution that is going to be the leading contribution to the adjoint sector partition function is going to come from this diagram. Okay, and you can see that because this is the one that goes as NF squared, which is the number of long strings that you're going to have, because their ends can be attached to either FZT brain. So the computation of this guy, actually there's a lot of discussion this already in Juan's talk of related issues. Okay, so the idea is that we use this equivalence to the deformation by the sine Liouville background. So then it's just the torus to point of two of such sine Liouville operators at finite temperature R, or finite radius R. Then you use T-duality to relate this to the one-to-one scattering amplitude at a different radius R prime. But now these are scattering of just the momentum modes. So this scattering amplitude you can extract, for example, from the matrix model at finite temperature and at one loop. So this is a known result. And if you do that, you arrive at this result with just a polynomial in the radius. And at least the first place I saw this computation was in the Kazakov, Kostov, and Kutazov paper. Okay, so that's the worldsheet prediction once you accept this deformation of the closed string background.
You can also get this result just by any continuation of finite temperature S-matrix elements written by Igor many years ago.
But weren't those were those also written for the worldsheet scattering amplitudes?
Well, I mean, it's from the matrix model. The matrix model, right? It is the finite temperature S-matrix elements and it continues and stabilized, but the formula is can read out from that.
Yeah. Okay. Sure. Okay, so that's a prediction from the worldsheet side, and now I just want to describe the matrix model computation, which is this work in progress. Well, the last part that's going to match this is the work in progress that I described at the beginning. So from the matrix model side, you're just taking the trace over the Hilbert space of e to the minus beta h. The singlet sector, you just have this non-interacting fermions. So the computation was done, for example, in this paper in the 90s. And the result is known to all orders. So now let's move on to the adjoint sector. Now you have NF squared types of long strings, because you can have NF FZT branes. So the computation of the partition function looks like this. You have the NF squared factor outside, and then you can have the thermal trace of one long string, or you can have one long string plus one closed string, one long string plus two closed strings, etc. And you have to sum over all of these. At leading order, this long strings and closed strings don't interact. So the closed strings just give you the singlet sector partition function. And then the long strings, you just get the e to the minus beta times their energy together with the inner product between two such states. And this is what should match the cylinder diagram, which is the leading order contribution. So this calculation was done by Juan in 2005. And so the divergence that I mentioned in the cylinder diagram, you can understand it here because, you have this inner product of scattering states. And this, of course, has an IR divergence. But it's also known how to regularize this. So once you subtract this IR divergent piece, you get the finite answer, which exactly matches the worldsheet result. Okay. So that's a nice check. There's also a subtlety associated with the energy shift in related capital E to little e. So the actual renormalized energy, but this is kind of constrained, and you can match it to the matrix model, to the worldsheet. Okay, so now we can go on to the next order computation, and now we have to consider interactions in the Hamiltonian. Okay. So the leading contribution comes when you bring down two factors of these interactions, because the leading order just vanishes. And then, once again, you have the thermal bath of closed string factorizes, but you can have different contributions. You can have a single long string interacting with this Hamiltonian squared, and then you take the bra with another such, I guess, just to be complete, I had e to the minus beta h. So I just did this expansion, right? E to the minus beta h 0, you have 1 plus minus beta h int plus dot dot dot. So you expand it like this, and the second order term is the one that contributes. So you have this first contribution. You can also have a contribution where the states that appear in the trace have both a long string and a closed string. And you can also have a contribution where you have two closed strings, but it's a finite sum. There's only finitely many terms that contribute. And this is what should be reproduced by this cylinder diagram with a handle. Okay, let me focus on this first guy here for simplicity. So the computation is straightforward. You rewrite it in terms of the renormalized energies epsilon, here and here. And then you insert a complete basis of state in between the interaction Hamiltonian. And the point is that, the only thing that appears there is going to be another long string together with another closed string. But I should emphasize that, this is not a scattering amplitude. So this epsilon prime and omega can be anything. It's a complete set of states. But the point is that we do have this Hamiltonian, H interacting, and we also have the wave functions for E. So in principle, you can go on and compute this matrix amplitude. And it's the same one that appeared in the tree-level scattering amplitude, in fact. So it's a work in progress to go on and compute this contribution together with these other ones that appear and show that this matches the computation on the worldsheet side of this torus with two winding insertions. Okay, and I'll end here because I'm already over time. But yeah, that's all I wanted to say.
All right, thank you. Questions?
Can I ask? So So far,
actually,
like,
sort of before you ask a question, should we just move the questions to the discussion session, or?
Yeah.
Well, since you're the board,
you're the boss. You are the boss, right? So.
Well, I'm making you in charge. What do you want to do?
Should we start the discussion session a little bit later, so that maybe 15 minutes later, so people can grab food or something, whatever?
Okay, yeah, let's do that. Okay, Shota, your question.
All right, thank you. So far, like what you presented, like explicitly was more like a perturbation of lambda in terms of lambda, right? And like you basically like gave a rough argument that this should also be true, and you can just resum it. But like from the string worship point of view, you probably need to do a little bit more, because like if you have a multiple holes, then like you're integrating over the size of the holes, and then you want to claim that each can be replaced by the vertex operators. But if you start putting a lot of holes, then the moduli of that surface is a little bit more complicated than just considering the cylinder. So
yeah, no, I agree. So the general argument, I mean, it goes along similar lines, but I also, yeah, I agree with you that it's not a rigorous proof, because maybe let me just quickly sketch the general argument. You know, it's like you can have holes, say like this, and insertions, and then you still expect a factor of NF for each hole, together with the coupling to the FZT brane, which has the cost for pi SP, or the sinh to pi p. And then you expect to have poles when the intermediate state goes on shell, so that should be associated to the propagator. You get this factor. Okay, and you have the sum over winding and